about Le Chatelier's principle. And at the core, what this thing gets at is when something is at equilibrium, if you think about kids on a seesaw, all right, um, you know, if you can put the right kid at the right spot, the seesaw will just sit perfectly still. But if anything comes along to disturb the balance, then in order to regain balance, you have to shift some things. You have to move some things around. So that's in essence what Le Chatelier's principle is, but it's just for a chemistry concept here. So when we have a stress that's applied to a system, and these notes are posted on today's class lesson, when we add a stress to an equilibrium equation, then what's going to happen is it's going to respond to undo that stress. And as we work through this, I hope that this makes a lot of sense. It's pretty cool to actually see. And to help us see that, all right, what I'm going to do is we're going to fill in this table here, and we're going to be looking at this actual reaction. So I'm going to be kind of toggling back and forth here between showing you this reaction and filling in this table here. So if I can pull this off here, Jack, I'm going to ask you to double check something for me. Are you seeing now my screen on the computer? Jack, you there? You're muted, my friend.
Yeah.
Okay, you see a lady in a red shirt getting ready to do some science? Oh, yeah. Okay, cool. All right, so check this out. And let me ask you this, Jack, do you hear her talking?
Reaction.
Oh, yeah.
Cobalt chloride.
Okay.
And it changes from pink to blue. And that's how you can tell what the shift is happening, what the color changes. It starts off this really light pink color. And that's if it's to the left. And if it's headed to the right, it's this really nice blue color. Okay, now in the middle here, I have 4 test tubes that are sort of right at equilibrium here. They're purple, so they're halfway between. And I'm going to add a stress, and I want you guys to predict what's going to happen. Will it shift to the left and be pink, or will it shift to the right and be blue? Okay, so the first shift I'm going to try, take my test tube, and I'm going to add some concentrated acid, some HCl. So what do you think is going to happen? On your paper, there's a place to make a prediction, so make your prediction.
Now, we'll just let this play.
Adding HCl. So which way do you think it's going to shift?
Right.
All right, let's see if you're right. I'm going to add the acid.
That's right.
And it shifted to the right.
Okay, so listen, let's go back and look at our notes here, because what's happening is pretty cool if you really think about it. Okay, so what we saw in the video, and here's the reaction, right? We've got a pretty complicated ion here. So in the video, what we did was we increased the amount of, we added some HCl, all right? So that introduced some Cl ions into the system. Well, if all of a sudden I come in and I increase the amount of Cl minus, all right? Now I have too much stuff on the left-hand side. So if I have too much stuff on the left-hand side, the reaction says, I got to get rid of this because now I'm out of balance. And so what that does is if I had too much reactant, right, it's going to shift the reaction towards the product side of things. All right? Because by shifting that stuff over, what I do is when I allow these two guys to come together, right, I'm going to end up with more of this stuff and less of this stuff. So that is the essence of Le Chatelier's principle. Chemical equilibria will respond to stresses, right? So what we saw was that we increased the amount of Cl, and it made more of a bluish color, okay? Now, I'm going to pause for a second. This is complicated at first, so as we're going through, I'm just going to kind of periodically check in with you guys. Jack, Stella, you guys okay with that first piece?
Yeah.
Yeah.
Okay, all right, so now let's think about the next one actually isn't shown in the video, but let's just kind of talk through this. So if I come along and I add H2O to this, okay, I'm all of a sudden putting more of this guy. So now all of a sudden I have too much reactant or too much product there. Either one of you. Too much.
Are
these the reactants or products?
A product.
Yeah. So if I have too much product, what that's going to do is it's going to shift the reaction in the other direction, because now I have too much on this side of the equation, and I need some more over here to get back to a balance point. So what color would we expect this to become? It was sort of purple. Would it go blue or would it go pink?
Pink.
There you go. No, you're exactly right. Because what it's doing is it's going to be shifting it back towards the side that is more of this. Okay. Now, the next one, all right, we'll make a prediction here and then we'll watch it. All right. So the next one, she's going to add some silver nitrate. And there's a little bit of a reaction here. It says, let's see, we've got the silver nitrate. Silver nitrate will actually combine with, right, some of this, right? So silver nitrate combines with this and it makes this guy. So in adding AgNO3, what I'm actually doing is I am pulling chlorine out of the system, all right? Because the chlorine is going to be a part of this little side reaction here. So think through this. If the amount of chlorine actually were to go down, now I don't have enough on this side of the reaction. So there's too little on this side. So I'm curious, which way does that then shift the reaction? Would the reaction shift towards the right to make more product, or would it shift towards the left to make more reactant? Anyone brave enough to take a stab at it?
I'm gonna guess it would shift over to the left.
So shifting to the left because we don't have enough on that side. What do you think about that, Jack? I think you're still muted. And if not, it's okay too. So Stella, you're right on the money, okay? What we would see is that it would go pink. So let me come over here and see it, and then we'll look at one or two other things here real quick. So I think I'm sharing it. Stella, give me the heads up. Are we back to seeing the video on the screen?
Okay. Put that on that side. All right, so acid made it shift right. Let's try something else now. I have silver nitrate, AgNO3. I'm going to add some of that.
So it pulls the chlorine out.
Why?
So we have too little on the reactant side. So we're going to end up needing more.
Shift it to the left, but there's something else going on.
And we're not worried about the precipitate, so I'm going to skip ahead here.
Stuff on the bottom. Okay.
Okay. All right. Now, let's do this. All right. Let me get back over to here. Complicated sharing of cameras here. Okay. Now, a couple little tricky things here, and then we're going to practice this a little bit. We have to think back to our unit on heat. All right. This is the symbol for heat. All right. So I've got a change in H for this reaction. This reaction has a positive amount of heat associated with it. So if we go back and we think, exothermic gave off energy, endothermic absorbed energy. Now, if I gave off energy, I would lose. So if I was exothermic, I would have a delta H that is negative, all right? That's not what I have here. So that means that this must be an endothermic reaction. And this is going back a little ways. That's why we're kind of refreshing our memory. So that means that for this reaction to occur, it doesn't give off energy. It has to absorb some energy. So here's what we have to do when we encounter something about a temperature change in an equilibrium expression. We have to know whether it's exothermic or endothermic. If it's exothermic, we're going to put a plus heat term over here on the product side, because exothermic, the heat would be a product. It's going to be given off, but that's not what we have here. So what we're going to do is we're going to add, and this will look strange at first because we've never really done this. We're just going to put a little heat term over here, okay? So this is telling me, hey, I have to put heat in. It's endothermic, it's got to absorb heat for this reaction to occur. Now let's think about how this would influence the equilibrium. If I were to all of a sudden increase the temperature, what I'm doing is in essence, I'm increasing the amount of heat. Now I have too much heat. And since the heat is on this side of the equation, right, this is where I need you to start thinking. So all of a sudden I have too much of something on this side. So which way would everything shift here? And Jack, are you still there? Can you get your microphone unmuted and give us an answer? If I have too much on this side, which way would that shift the reaction?
Gonna go to the other side.
Exactly. So we're going to favor the formation of, and are these the reactants or the products over here? These are the...
Those are the products.
Yep. Beautiful. Okay. So we're gonna shift the reaction to the product side. And since we're shifting it this way, what color would we expect here, Jack?
Blue.
Yep. Yep. And so Jack, thank you. And Stella, let's go back and think about what if I decrease the temperature of this equilibrium? Now all of a sudden, instead of having too much heat, I don't have enough heat. So I lowered the amount on this side. I have too little over here. Stella, which way would this shift the equation? You're still muted there. Yeah. I don't have enough on this side of the equation.
So it would shift to the left.
It would shift to the left, and that's what I'm doing with these little curvy arrows. It's saying, hey, I need more on this side, or I need more on that side. So I'm going to favor the formation of some more reactants. And so what color would we expect to see there, Stella?
Pink.
Yep. And in fact, if we went back and watched the video, that's exactly what we would see. Okay. So we're starting to get a feel for how things respond due to stresses. All right. If we can change the amounts of things, or we can change temperatures. So those are really cool things to think about. All right. Now let me pause for a second before I move to the next page. Any questions you want to ask about?
I don't have any.
Okay. All right. We'll continue here. All right. So this, and again, this is in the notes. It just summarizes all the stuff that we just walked through. So I'm not going to read those things to you. All right. But this is an important point. All right. A couple of days ago, we did some problems where we wrote some equilibrium expressions, those K expressions. And you have to remember that we never include pure solids or pure liquids in an equilibrium expression. And because pure solids and pure liquids don't appear in the equilibrium expression, if we mess around with the amounts of solids or liquids in an equilibrium, it doesn't change anything. If we go back and we look at the reaction that we were just looking at, notice that all of them were aqueous, right? So I had no pure solids and no pure liquids. And we'll look at an example with pure solids and pure liquids. And that is there just that messes with you, okay? One other important point, all right? The only thing that is going to change the equilibrium constant, the actual number that K value has, K is equal to some number, right? When you write that equation, you put the numbers in, K is just equal to number. And the only thing that changes that number is the temperature, all right? And we'll talk more about that in a minute. So unless you see a change in temperature, K stays the same. All right, now one last one, because what we've not talked about is the funny thing that goes on with gases. All right, now let's focus in on this guy right here, this equation. And Stella, I'm going to come to you with a question. How many moles of hydrogen do we see reacting in this equation?
2.
We see 2 moles of hydrogen. That's perfect. Now, not only is it 2 moles of hydrogen, it's how many moles of oxygen, Stella?
Only 1.
It's only 1. So if I asked you how many total moles of reactants are there? It's a total of? Would you agree with 3 moles of reactant? Because 2 plus 1 is 3?
Yeah.
Okay. Now, Jack, we're going to make how many moles of product here?
2.
2 moles of product. All right. And this is really important when we're talking about gases. All right. This is only for gases. So think through this. If I have a certain container, all right, and I allow this reaction to occur, it's going to find some sort of equilibrium. Now, if I change the size of the container, if I make the container all of a sudden smaller, which is what I'm saying here, let's go from 2 liters to 1 liter, right? I now have less room for gases. So what an equilibrium reaction will do is it's going to say, well, wait a second. If all of a sudden I have less room, I'm going to go and I'm going to favor the side of my reaction that has, in this case, because I have less room, I want less moles of gas. So in this problem, by decreasing the volume, what I would see is that the reaction would shift to the right. And that would mean that I would have more of this and less of this. If it flips around and instead of going from, let me slide this up, instead of going to a smaller container, if instead I went to a larger container, now all of a sudden, made it big, and I'm going to now have plenty of room for more gas. So the equilibrium reaction, instead of shifting in this direction, it's going to shift in the other direction because this one has more gas. And the reason that it shifts in that way is because now I have more space for gas. So the shift would be in the other direction, okay? Now, if we had all the time in the world, we'd start to talk about why this is so important. But what I do want to do is jump in here. So let me pause for a second. So gases is sort of the last little piece of this. Questions before we practice this together?
No, I don't have any questions.
Okay. All right, so let me go ahead and shift over here. Okay, let me see if I can find my file. Oh, darn it, hang on. That's not it. Sorry, guys. One of these days, I'll get really good at doing all of this. There it is. Okay. Hey, can one of you guys tell me that you see a little sheet that says Le Chatelier's principle continued? Le Chatelier's principle? Yeah. Okay. All right. So cool. Check this out. All right. So what we're going to do is we're going to think about this particular reaction at first, and we're going to answer a series of questions. And this is the assignment that I posted for today. I'll give you guys Monday to work on it as well, because we're getting close to 30 minutes on this. And so if we look at the example here, if I, and I think you guys can see my cursor as I wiggle it around. Does that sound right, Jack? You guys see it there, Stella and Jack?
Yeah.
Okay, cool. So if I add into, that means I now have too much on this side of the reaction, which means it's going to shift it to the right, all right? And so what we're going to do, and this is the case for all of these questions. So since I'm adding N2, I don't really care what happens to the amount of N2 because I know that it's going up because I'm adding it. But if we think through this, if the equation is shifting to the right, that means that I'm making more of this, and I have to have this reacting to make this. So the amount of H2 has to go down because it's being consumed. It's being used up to make more of this guy. So that's why we're saying that the amount of H2 would decrease, because as the H2 and the N2 combine, it's making more of the NH3. And then the last one here in the example is, since I didn't change the temperature of the equation, K remains the same. The only way I can change K is by changing the temperature. So let's see what this looks like if we were to tackle one. So let's add H2. Now all of a sudden I have too much of this. That means I have too much on this side of the reaction. And can either one of you tell me which way would this shift the equilibrium, to the right or to the left?
Right.
Absolutely. So what's going to happen? We're not worried about what's happening to H2, but if I'm making more of this, what has to happen to the amount of N2? You want to take a stab at it? Okay, if we don't.
It's going to decrease.
It is going to decrease. Well done. Because it has to get used up by combining with the H2 to make this. So what I would do is I'd either draw a down arrow here, or I'd write the word decreases. And then what's going to happen to the amount of NH3 over here? It's going to increase. Did the temperature change in this one? Absolutely not. So here we would say that K remains the same. All right. Let's play this one. All right. We add some NH3. Now all of a sudden I have too much on this side. So the shift should go to the left, which means I'm going to have more N2. So I should say increases, or draw an up arrow here. I would have more H2, so it increases, up arrow, and then K remains the same. We'll do just one or two more here, and I think that is at least enough to get you a start on this. All right. Okay, now, because these are all gases, all right, we do want to be careful as we get down towards the bottom here. If I take N2 out, Stella, which way is that going to shift the equilibrium?
To the left.
Perfect. So what's going to happen to the amount of H2 if all of a sudden I am making more of this side? H2 is going to
Go up. Increase.
go up. It's going to increase. So H2 would be an up arrow, increase. Stella, what's happening to the amount of NH3?
Decreasing.
It's perfect. And what would K do?
It would stay the same.
You guys are knocking it out of the park. Okay. All right. So here is your task, and I'm going to go ahead and stop the video here. Hopefully that's enough to get you guys rolling with this.